Let's take a look at auditing software. Auditing software includes ensuring we have adequate licenses to cover all of the users we have, but also making sure we have not invested in licenses we're not using. In some cases where we have bought software from a vendor and we don't have the actual source code itself, we may want to protect our interests by insisting that the vendor then keeps a copy of that source code in escrow. This will allow us to protect our interests, so if the vendor fails to live up to the terms of their maintenance agreement, that we'll be able to get a copy of that source code that we'll be able then to use to maintain for our own purposes. An important part of software also is the protection of then version control, making sure that we always have the latest version, we have a record and document of all the changes we've made, that we also ensure that any changes we make do not overwrite previous changes. We want to make sure we always have the latest version, but we'll also, of course, keep some of the former versions as well in case we need to roll back. It is important that our documentation is up to date. What are the changes we've made? Who approved those changes and what was the purpose of them? How did we test to make sure that those changes work correctly? An important role of the auditor is to ensure that there is this proper control over then software. We need to protect our source code. Our source code is what is used then in building and compiling our various programs, or interpreting, depending on the type of program it is. And we need to ensure that no one is able to affect or change that source code except through very carefully controlled change management processes that would require then the oversight, approval, and moreover, separation of duties to any changes that were being made. One of our most important but also most vulnerable types of software today are web applications. Web applications face the outside world and therefore very often are subject to different types of attacks. It's important that we build web applications to be secure, stable, and resilient to an attack. One of the most important controls that is built into a web application is input validation. We cannot trust anything that comes from outside. We have users that log into our web applications, check our products, order products, pay bills, and all of the input they provide to us also provides an entrance for a potential attack or even corruption of our data and systems. One of the most important areas we need to do is ensure that we've put in validation for all input. Is that input allowable? And also to ensure that we do this both at the client side as well as at the server side. Anything that is done out at a client can be manipulated by the client. Therefore, that same input validation that was so critically important out on the client's browser must be repeated now when it gets to the server to ensure that now at the very edge of our defense, we are going to protect our systems from any type of an attack. We should also validate and ensure that any output that goes out also is valid. This is where we'll use many different types of processes and encoding and other types of whitelists to try to ensure that we limit the attack space that could be used by an attacker. One of the most important parts of web application security is to install a web application on a bastion host. A host that is hardened with minimal numbers of different types of administrative interfaces, that is often a screen subnet that is protected so that there's a very limited attack surface then for the web application itself. We'll put it in behind firewalls and quite often web application proxies, but we'll make sure that the web application and the host that it's running on are always hardened and isolated from the rest of our internal network, so that even if there was a compromise of the web application, it would not result in a compromise of our internal systems. An important part of web application security is also session management. And session management is to ensure that a person does not leave a session open for an extended period of time. No, after a few moments of inactivity, it'll lock out. If a person tries to log in repeatedly with the wrong password, we'll lock out that account for a time period. And in some cases, we'll lock out the IP address from which that attack is coming. This will allow us to ensure that an attacker who's trying to break in is going to be, in many cases, at least stymied or slowed down. We could create things like tar pits and honey pots to try and draw an attack off in another direction. When it comes to network infrastructure, we have many different types of networks. Very often in the old days, our computers would talk to each other over dedicated networks that were not connected to the internet. Many of our SCADA or industrial control systems also ran on dedicated networks. These were often known as like leased lines, for example. And the advantage of those is that they were a private network, and as such, were not subject to many of the attacks of the networks of today. We also used to use a lot of circuit switching. This was used especially in the telephone system, the plain old telephone system, sometimes known as POTS, or the publicly switched telephone network, the PSTN. The PSTN operated on circuit switching, where we established a connection between the two parties that were communicating. And that circuit or that connection remained established for as long as they communicated. This allowed a fairly reliable and consistent level of service over that circuit. The disadvantage of circuit switching is it's rather inefficient, as well as, in many cases, it was rather expensive from the perspective of bandwidth utilization. Today, we mostly use packet switching. We use things like we moved from X.25 to frame relay, ATM, and over top of that running, of course, MPLS, multi-protocol label switching. And these packet switching networks work very much like the highway systems of today, where we have many roads going between towns, and you can decide which road you want to take. Do you want to take the fastest road, the shortest road? As we know, sometimes the highway is not necessarily the shortest route. However, it might be faster. And packet switching is where we have, say, 10 vehicles that need to go from one building to another. They all leave from the parking lot at the same time, and they all find their way through the road networks towards their destination. The difference with, of course, packet switching is each car may take a different road. They may, out of order, come. And so this is where we have to do things like buffering and fragmentation. Take all of that information we have to send, break it into individual packets, label each one, send them out across the network, and at the far end, buffer and reassemble them back into order. Now, the difference with packet switching is it can tend to be more efficient. We know, for example, it's much more efficient than when we have shared roads that everybody can use, rather than just having one road for your own personal use. However, this also means that we have a lot of variation then in service. Sometimes the traffic goes quickly, and sometimes it's just hopelessly slow. But one of the advantages of packet switching is that if there's construction or if there's any type of disruption on the network, then usually we can route around it, find a different way to get towards our destination. We have a number of different tiered networks today, multi-tiered networks of various layers, we can say here, that will allow us quite often to have a data layer, a logic layer, a presentation layer. We often call these 2- and 3-tiered networks, and this allows us to, in many cases, provide a separation between what the hardware does and how we manage the use of that hardware via software. You take, for example, a virtual LAN. A virtual LAN is one switch that we can actually logically separate into a number of different, should we say, networks. So even though it's physically one device, we can manage it through software to operate as if it was 3 or 4 different devices. So some of our types of networks Obviously, as auditors, we have to have at least a cursory understanding of these types of networks so that we can effectively audit. You have personal area networks, such as, 802.15, the IEEE standard for Bluetooth. And a personal area network is when I've just connected two devices together, such as an earpiece and a phone. And that, in this case, would be a wireless personal area network. Bluetooth being fairly short range for the most part, operating the 2.4 gigahertz bandwidth. And of course, what are the challenges with this? Well, can somebody associate who shouldn't have? Another problem possibly with a personal area network, could we have a problem here that somebody can jam the signal? And this is where we're seeing a little bit of a problem today when it comes to things like cars that are then you can operate with a remote key. What if somebody jams that signal and I'm not going to be able to lock or unlock my car effectively? We need, as auditors, to be thinking of the types of risks and the things we have to do to protect the stability and availability of network communications. Now, one of the problems is that many of these terms they're not exact. For example, what is a local area network? A local area network is best defined as a network of devices within one geographic area. Now, a local area network can be anything from 2 devices to several hundred. It could be in one floor of one building, or it could be in one building. It's just basically representing at least a network within one local area and often under one manager. However, local area networks themselves often are then broken up into virtual local area networks, where we can separate off, for example, if we have a company, we can separate off the part of the network that supports finance from the part that supports HR, and isolate the part that supports sales from the part that supports operations. This idea of setting up virtual LANs allows us to protect where does the traffic go. We want to isolate so that HR traffic is not visible to people in sales, for example. This can help us both with better bandwidth utilization and a little bit more security as well. We then have storage area networks, or SANs. And a SANs is usually a network that's set up as a way to provide storage services or backup services for a number of other servers. Very often a SANs has its own network that's not being used for production data transmission. Very often, in fact, that network used in a SANs will be a fiber fabric and so on. So that all of our servers can be backed up to one, say, common place that provides then that support and backup services for all of our production systems. And then we have wide area networks. Well, wide area networks are when we're connecting local area networks together over a greater distance. Now, you have others you can bring in here, campus area networks, which are several buildings, such as a university, that are linked together. You could have, of course, metropolitan area networks, as quite often all the buildings within a city area that are linked together. But sort of the outside edges, the LAN being the very local area network, and the wide area network, the WAN, being where we're connecting different LANs together. We're able to send traffic between cities. And very often a WAN is using then facilities provided by a telecommunications carrier. I don't usually control that roadway between then my local area networks. I'm instead renting a service or leasing a service off of a telecom carrier using things like asynchronous transfer mode, frame relay, MPLS. X.25 is really at end of life, though there is still some of it in use, part of our original packet switching equipment. So when we are going to audit a network, we have to audit according to what are the priorities, the requirements of network communication. And this is the area where we hear so much about 5 nines availability. Availability that means we'll have availability 99.999% of the time, which means that our network has to operate at a level of reliability of only, should we say, seconds worth of outage within a month. But we also have to have all these devices talk to each other. We need interoperability between different pieces of equipment, different systems, and even in different countries. We have to be flexible enough to deal with changing business needs, to be able to add on bandwidth when necessary, or in some cases meet peak levels of demand. In some cases, of course, when it comes to flexibility, we have to be able to change our routing when there's been a problem, say, for example, on one network segment. Now, in addition to this, of course, we still have to provide for the confidentiality of traffic that is going across that network, and we have to provide, of course, then for the integrity of the traffic, that it's not being corrupted or changed in transmission as well. This requires careful network management, and this is where many organizations really struggle. Their networks have been built together by a number of different pieces that have been kind of added on to each other over the years. So therefore, there's often not a cohesive architecture. There's often different vintages of equipment, different styles of systems, and many companies, frankly, don't even know what they have. So network management is this area now of not just having things run, but really managing how the network operates, working towards better levels of oversight, governance, watching out for things like single points of failure, proper access control, and isolation. Now, one of the things that makes the internet work today so well is the domain name system. One of the nice things, if you want to go to ISACA, you just have to know to type in isaca.org. However, obviously the routers and the devices on the network itself, the internet, have no idea who isaca.org is. So therefore we have a very good tool known as DNS. And DNS contains the cross-reference between then a normal address or name such as ISACA and its true IP address, which is the address that is really used on, as you say, the internet itself. So when I, for example, at my organization type in www.isaca.org, that request goes up to my DNS server, and my DNS server out at the perimeter of your organization's network takes a look at it, shakes its head, and says, I have no idea who that is. So it sends a request up through the DNS tree, and the DNS is arranged as an hierarchical model. It calls up to a higher level, well, right up to a top level domain, or TLD as we call it, and says, does anybody out there know who isaca.org is? What will then happen is the device that is hosting isaca.org will reply back all the way back to my DNS server, and my DNS server will dutifully write that down in a table that says, okay, this address belongs to that IP address, so therefore anytime in the future that somebody says, I want to go to isaca.org, I will know just to convert that into this IP address so that traffic can be routed. Now, obviously, one of the problems for us as auditors is we have to make sure this is working. We have to make sure that we don't have susceptibility to things like DNS poisoning, where somebody can then poison the DNS so that now traffic gets sent to the wrong place. We also have to make sure that DNS server number one is available, because for most people, if DNS doesn't work, the internet becomes useless. And the other, of course, problem with this is that sometimes DNS entries can give away information about the company. We need to make sure that we have proper precautions in place. Maybe we are using things like DNSSEC, which is DNS security, or we watch out for things like zone transfers. These are all things that we need to do and make sure that our organization is watching for as well. The other thing, of course, is make sure we've always registered our domain names. You don't want to find out that all of a sudden the domain name you have, somebody forgot to renew its subscription, and now somebody else can take over our domain name. When you first connect to a network, you walk into an organization, or even a Starbucks if you wanted that. You open up your laptop, then you have, of course, on your machine, you have your MAC address. Your MAC address is the media access control address. That's the real hardware address of the card in your laptop that will communicate out with networks. And that MAC address on your network interface card is a 48-bit address. But if you're going to talk to the internet, you're going to need to have an IP address. So your device now calls out to the DHCP server. This stands for Dynamic Host Configuration Protocol. And the DHCP server receives this DHCP request from your laptop. And it looks up what IP addresses it currently has available, and it quite often will give you an internal address. We call these from the RFC 1918. They're non-routable internal addresses. For example, the entire 10 series, anything that's 10 dot whatever. Or very often you've seen your IP address be 192.168. These are some of the addresses that are often used for internal IP address management. And that is through a process we call network address translation and port address translation. So the DHCP server replies back to your laptop with a DHCP offer. Here you go. When you get a DHCP offer, your laptop accepts that. Now, that IP address that was just assigned to you will be then leased to you for a certain length of time. And depending on the organization, might be anything from a few hours to, of course, a week. And this allows us now to assign you an IP address when you walk into another place. However, you also know the problem with that. The other problem with that is that you leave that Starbucks and go to an airport, you're going to be assigned a new address. This is the difference between logical and, of course, physical addressing. Your MAC address on your laptop is a physical address. And you can be given a different IP address when you're in different buildings. And one of the things that also is necessary for this to work is, of course, address resolution protocol, which will then be that cross-reference that's used, keeping a list of which IP address is currently associated to your MAC address. Mostly today we're using IP version 4, where our IP addresses are 32 bits in length. We usually write them as 4 octets. But we're kind of running out of IP version 4 addresses. And in fact, today purchasing them can be a rather expensive endeavor. So more and more we will migrate towards IP version 6. With IP version 6, we will have a completely different networking scheme that instead of writing the IP address now as 4 octets, we will actually write it in hex because the IP address is 128 bits in length. To give you an example of what that means that everybody on the internet today will be able to have an address space of their own, the size of today's internet. So when we go to IP version 6, we've caused an immense increase in the number of addresses that are available. This means we should not run out of IP addresses for any time in the foreseeable future. And of course, IP version 6 also has a few additional benefits in the performance and so on of it and the security. We said that your address, the true physical address of your machine, the media access control address, or of course we could call the address of your NIC card, network interface card, is then that 48-bit address that is really consists of the vendor and the serial number of then the network interface card in your machine. That is your physical address to which you will then be assigned an IP address when you're trying to go out on the internet.